Hey guys, welcome to chapter 6 where we're talking about work and energy. And so the first section we look at is going to be work done by a constant force. So that simply means whenever there's an object, we apply a force on it and it moves. So now we're going to consider what happens when we move it across a certain displacement or distance. So we have the definition here: work is done by a constant force multiplied by the component of force in the direction of the displacement. So we know that as FD cosine theta. And so when we say that cosine theta, it sort of depends on where the angle is set up. So here's how we'll kind of look at it. Here's my mass, my orange block there. And I have a force applied to the right over a certain distance. Notice in this case, this is how we usually start the problems out. Force times distance would give us the work done here. When I have the same mass, but I apply an angle to it, that theta right there is the parallel component of it. So we only look at the parallel components, or the force along the displacement that the mass is undergoing. That's how we calculate the work. So in the SI system, the units of work are joules. So a joule is 1 Newton times a meter. And if you also notice the energy is also in joules. So work is energy is work, and both are labeled in joules. And so we have an interesting things that can happen here. So have a mass here, and let's say I apply a force to it to hold it up, and I have a weight of it, obviously. And what I do is I carry it along a certain displacement d. So here's an interesting thing: as long as I don't lift it or lower it, no work is being done on it, because the FG and FP are perpendicular to the displacement d. Now, obviously, you're spending energy working on holding the thing up. But once again, work is defined as FD cosine theta, so the forces FP and FG individually do no work. So that's something we'll have to look at and consider. So work can be negative, but here's an interesting thing first. We just talked about centripetal forces and how they apply to keeping things in motion. Here's an interesting idea. If an object is in circular motion, it has both the FG, but its motion is always parallel. So that velocity is always parallel to any force that's applying to it. So technically, no work is done on an object moving in circular motion. That's kind of why the planets stay where they are for the most part. There's no extra work being taken away from them, like air resistance. That's friction. That's kind of what this little slide here says. So I don't ever have to add work to it. There's nothing ever being taken away from the system, which is an interesting idea. But work done that oppose motion, friction, will be negative. So here's the idea. I have my mass, I have my normal force and the weight, and then I have my direction of motion, my displacement d. And let's just say for this example, I have an applied force at an angle. And let's include friction. So friction would be pointing to the left here in red. So it's going to be negative work, or in other words, it'll take energy away from the system here. We calculate work the same way. Work done by friction is how we would say that, is the force of friction times the displacement. We also force of friction, mu times normal force, so we might have to go in there and grab some extra variables or calculate a few extra things. So just as a little quick introduction here to work. So when we come to class, we'll have a few questions to work on. But I hope your long weekend is treating you good. I'll see you guys later. Thanks. Bye.